in this problem, our assignment is to find V0 and V3. You can see we have 2 op amps. You can see V3 is labeled and V0 is labeled. Again, we're going to use our problem-solving strategy on op amp circuits. And remember, we assume an ideal op amp where the current flowing into the terminals on these op amps is 0. The voltage difference between the 2 terminals is 0. So let's substitute in our op amp model and redraw the circuit. So here's our circuit. You can see when we put the op amp model, substitute the op amp model in, there's where the op amps were. We can see the current's 0 on these terminals. We enforce that by showing an open circuit. Now let's define this voltage as V1, and I'm going to define this voltage as V2. And now let's apply Kirchhoff's current law at this node. So if we do that, we have V1 over 5K plus V1 minus V2 over 10K equal to 0. And if we multiply through by 10K, we'll see that we have 2V1 plus V1 minus V2, and we get V2 equal to 3V1. Okay, also, if we look at this node, we can see the same current. If we call this current, for instance, I2 also flows through here because this current is 0, so we can relate V3 to V2 by voltage division. So then V3 is 10K over 10K plus 2.5K times V2, and if we calculate that, V3 is equal to 0.8 times V2. So now we've got relationships between V2 and V1, also between V3 and V2. So let's continue our analysis. And here's our circuit. We've defined this voltage as V1. So the voltage at this node is also V1. Here's the voltage V2. The voltage here is V3. Now, let's apply Kirchhoff's current law at this node. And if we look at the current flowing in that direction, we have V1 minus 5 over 5K. The current flowing this way is V1 minus V0 over 5K equal to 0. So the voltage V0 is here. So since the current flowing into here is 0, if I look at Kirchhoff's current law here, then the voltage V0 is across that series combination. So if we multiply through by 5K, we'll have V1 minus 5 plus V1 minus V0 equal to 0. So that'll give us 2V1 minus V0 equal to 5. Okay, so there's a relationship between V1 and V0. Now let's redraw the circuit again. Now, since we have V1 here, this is V3, and this is V2, let's now come back and apply Kirchhoff's current law at that node. So now we'll have, flowing this way, V3 minus V1 over 2K plus the current leaving through there is V3 minus V0 over 3K. And if we note that's 0, because again remember that current at that point is 0. Now if we work on this equation, we can collect terms. V3 times 1 over 2K plus 1 over 3K is equal to V1 over 2K plus V0 over 3K. And if we multiply through by 3K, we'll have V3, we have 1.5 plus 1, 1.5 V1 plus V0. So we have 2.5 V3, 1.5 V1 plus V0. Now if we divide through by 2.5, we get V3 is 0.6 V1 plus 0.4 times V0. And if we remember earlier that we had calculated V3 equal 0.8 V2, we substitute that in, well, let's see, let's substitute that V2 is 3V1, so that gives us that V3 is 2.4 V1. So now we get 2.4 V1 equal 0.6 V1 plus 0.4 V0. And we have 1.8 V1 is equal to the 0.4 V0. And if we simplify that a little bit, we'll have V1 is equal to the 0.4 over 1.8 V0. And previously we had derived this expression. So now I'm going to substitute in for V1, so we'll have 2 times 0.4 over 1.8 minus 1 times V0 is equal to 5. And if we solve this, this will give us V0 equal to minus 9. So now calculating, we have V1 0.4 over 1.8 times minus 9, so that gives us V1 equal to minus 2. And we also have already derived that V3 is 2.4 V1, so that's 2.4 times minus 2, which is minus 4.8 volts.